saying that we can start the session. I'm seeing 4 colleges here. Okay. Okay, I'm getting other responses also. I think, yeah, let us start the session. So, we are into finite element modeling chapter, and we so far we covered element types, modeling with various types of elements 1D, 2D, 3D, and also we discussed about element quality. And this session is about mesh convergence, information about mesh convergence. Yeah, what exactly mesh convergence is? Basically, in finite element method, we usually discretize the geometry into number of finite elements, and of course there will be some governing equations about displacement of formulation, and it will give an approximate answer. It won't give accurate answer. But then the question comes: how is that approximate solution? How much is the accuracy of that approximate solution? 5%, 10%, 20%? What is the accuracy with respect to the actual solution? That is the one question while performing finite element modeling we'll be having. So, and then the discretization mainly depends upon geometry of the structure. Apart from loading and boundary conditions, uh, the discretization, like number of elements in the geometry, it usually depends upon geometry type. For example, if you see that one more here, we have one model here with fillet. So generally, like when you subject a loading on this type of geometry, so these are highly stressed locations, and these locations, because they are highly stressed, they are area of interest. Because why they are highly, geometry is changing from where the area is changing from large to small here, and because of this area change, these locations are very critical. So actually, like if you put mesh here, very fine mesh, a coarse mesh, the result may not be accurate because it's not capturing the geometry. So we need to make sure that the discretization will allow us to put a very fine mesh here, so that it will capture the results, the physics of the problem and geometry of the problem. So basically, plate with a hole is again, when you try to apply a load like this location is highly stressed location. So we need to make sure that this geometry is captured properly, and we have put number of elements, sufficient number of elements in this geometry. So basically, discretization, what I mean to say is the discretization mainly depends upon type of geometry and what are the critical areas in the geometry, and those things will drive our Acae modeling strategy. Let us take this example: plate with a hole. So, as we discussed about this plate with hole, it will have two symmetries here along x-axis and y-axis. So, and we can model this geometry like this. Okay, 1/4 of model we can take it, and then we can do the finite element model. Here there are two types of meshes are there. One is coarse mesh, that means element size are bigger, and there is a fine mesh. Because this is a highly stressed location, and capturing this geometry and capturing number of elements such a way that will the stress prediction should be very accurate. In the sense, it should be very near to the actual value. So so this is one type of mesh. We put very coarse mesh here, and then what we did is, maybe so we put a variable mesh here. Like actually at the hole we put very fine mesh, but at the ends we have put very bit coarse mesh, because the reason is, here putting fine mesh here may not be required, because this is not our area of interest and we are not seeing any high stress here, but we are seeing very high stress here. That is the reason we have put very fine mesh. This is a strategy we need to follow. If you do any finite element modeling, you need to plan such a way that the critical locations where we get high stress, and important locations like fillet locations, hole locations. So these locations are tend to have very high stress, are subjected to high stress. So those locations we need to capture with the finer mesh details, and locations which are not so critically loaded, and which are not our area of interest, we can do with the coarse mesh. This is what we have done here. So we have put a very fine mesh here and we have put very coarse mesh here, and there is a very good nice transition from fine mesh to coarse mesh. So this is a very important strategy for whenever you do a finite element modeling. So now comes the topic related to mesh convergence. So in convergence, as the mesh size is reduced or number of elements increased, there appears to be some result will be getting converged. So as you keep on increasing the number of elements, let us start with say this location. Here we get a bigger variation. This line indicates exact solution. This straight line indicates exact solution, and this curve is related to number of elements. So as the number of elements increased, the variation with respect to the exact solution gradually decreasing, and and at certain point it will be almost stable. So we won't be seeing any much further improvement. So this location is where the convergence of the finite element modeling is achieved. This is what we so as you increase further from here, we won't see much improvement in the results, change in the results, very minimal change in the results. That's how, like, mesh size is directly impacting the results. So from this picture, it is very clear that we should be able to put finite element mesh with optimum size and optimum number of elements. So to achieve that, we have two direct methods. Two methods are there. One is calculating error in the mesh. So how much? So when you do a finite element modeling and you do the analysis, um, the tool will calculate the error, how much error present in the model, finite element model. That is one approach. That is one approach. Second approach is doing iterations by changing the number of elements. These are the two methods we typically follow whenever we do finite element modeling. Now coming to the refining a mesh. So in finite element analysis, solution accuracy is judged in terms of convergence. Uh, Suppose if it is not, if you are unable to achieve a convergence, suppose if we try to model a geometry with some mesh size and we are unable to get the convergence, then we need to do the remesh. So there are two techniques available. One is H method and another one is B method. So basically, whenever you do the mesh, we get a error estimation, and this error estimation usually provide the guidance for the mesh revision. So suppose when we do the meshing here, we check the error estimation in the geometry in this location. So if we get a like error within the limits, allowable limits, then this mesh is converged. Otherwise, we need to go for remeshing. So usually when we do this type of models, so the convergence usually checked at the or usually like convergence we need to achieve more at the location. So what we need to do is we need to concentrate more on these locations where we'll change the mesh. We'll refine the mesh at these locations. So next slides I'll be discussing more on what is H method and what is P method. So basically in H method we generally add number of elements or indirectly we are reducing the element size. For example, this is baseline geometry which is having 4 elements. So in iteration 1 we increased the number of elements to 16 and then we further increased this number of elements to 64. This is called H method. This is what typically we follow in most of the stress analysis. So some of the important things are like sometimes most of the times we'll follow uniform mesh um, and sometimes we'll go with a non-uniform mesh. That means uniform mesh means suppose I can give element size for this complete geometry as say one value. Say, let us give one. Or so for this one we'll get a mesh convergence at all at these critical locations. Otherwise, we can do another approach using non-uniform mesh because we know our critical areas are this here. These two areas are there. Here we can give element size 1. Here we can increase our element size maybe 2 or 3 or 3. These locations we can put coarser mesh with a large element size, and these critical locations we can reduce the number of size. So we can use either way. You can put a uniform mesh or you can put a non-uniform mesh. So basically the advantage of non-uniform mesh is we can reduce the problem size because we are mainly focused about critical locations. We are not focused about these locations. So putting finer mesh at these locations is waste of time and waste of rotational uh, time also. So usually like putting a non-uniform mesh is a smart modeling technique. So yeah, it's the same thing like mesh refinement continues. We get um, uh, results till we get a convergent results, or other way, the results occurred in previous iterations matches with the current iterations. So let us start with the like we have performed the iterations. Iteration 1, iteration 2, iteration 3, plus okay, iteration 1, iteration 2, iteration 3, iteration 4, and iteration 5. So we perform the iterations till we get prior iteration, last iteration results matches with the current rate. Suppose if I go to fifth iteration, the stress value of fifth and fourth iterations are almost same. That means mesh has been converged in iteration 4. So iteration 4 model mesh. So iteration 4 model mesh has been converged and it can taken for the analysis. So, and another point is instead of refining, we can enlarge the mesh also. It's a same way like suppose if I put very fine mesh here, then I'm after doing some iterations, I observe that this much fine mesh is may not be required. This can be size mesh can be increased further because it is not adding any importance to our results. This is the H method technique. And another method is P method. Basically, in P method, we won't remesh the geometry, and instead of uh, remeshing, we will increase the polynomials. That means, remember we have studied about linear and quadratic geometries, quadratic functions. So linear elements will have linear quadratic elements will have better convergence than the linear elements. So here we'll be adding additional polynomials to the element. This is the linear element, and here we have added two additional polynomials. Generally, like in P method, they'll add additional polynomials, additional two polynomials compared to previous one. So as we already studied the difference between linear and quadrature, um, and quadrature will definitely higher polynomials, elements with higher polynomials will give better results, and convergence rates are much faster. So this is called P method, and most of in P method employed by the computer programs, they will do it automatically. So not so basically we need to set up the option. We need to click on that option like add polynomials to that elements. So it automatically adds into the analysis. So basically we won't change we won't be changing any mesh here, but we'll be adding nodes, and there will be additional diagram to the nodes, or sometimes there won't be any additional degrees of nodes. Degrees of freedom will be added to the current existing nodes. That technique is also there in P method, so it will be either way. But in general, whatever tools I worked like ANSYS or LSDyna, they don't use this P method technique, or at least we are not using this technique. We use most of the time H method. So coming to error estimation, so whatever we discussed is related to the mesh refinement, but instead of doing mesh refinement, we can straight away check what is the results we can get in the current finite element model. So basically in types of error, like there will be bugs in the software. Typically bugs, sometimes bugs may halt the execution, and sometimes it will allow execution create inaccurate results. Even like we have been working in ANSYS for almost 10 to 15 years. At least I'm using from past 12 to 13 to 15 years. So most of the times we won't see the bugs, but some of the typical problems or critical problems we usually see the bugs that will report to the ANSYS team. Then they will come up with the solution to that bugs. So generally, like bugs in a software is pretty common. It is only we need to understand whether bug is there or not. It will come with the expertise, and there will be user-based errors, modeling error, and discretization error. These are some of the errors, common errors um, in finite element models. So in user error, like mistakes, usually like The software user will make uh, the mistakes even after understanding the problem. Like typically, like most other thing at times, user may pick wrong element type, or element sizes may not be appropriate, may not be correct element size he picked, or he might have applied wrong loads and boundary conditions. So usually this error is purely based on user skills. Suppose if a person worked on almost 15 to 20 years, if you give a problem, he will solve straight away. But if you give a problem to a newcomer, and if you give all, even though if you give all the guidelines, definitely will make mistakes. So this error is purely skill based and depends upon the user experience level, and it is nothing to do with the software or finite element method. And then comes modeling error. Basically, modeling error is the difference between physical system, actual what is the actual system, and what is the representative model in finite element model. That is mathematical model. Um, Generally, FE model is a simplified mathematical model, and this mathematical model is a accepted mathematical formulation, and most of the times, like we'll be omitted finer details. Suppose generally while doing finite element modeling, prior to that we'll clean up geometry. The cleanup is carried it so that our we don't have any issues with the geometry and we don't put too many finer details. For example, like let us take same example. Okay, suppose in cleaning up geometry there is an important step called defeaturing. So we generally defeature very small fillets. If you see here this fillet is very big fillet. Suppose if I want to defeature it, then this looks like this. If I defeature this fillet, it looks like this. So when you try to apply load, definitely very high stresses will be generated. So this is very bad modeling strategy, defeaturing this. But sometimes what happens, and this should not be done. So if you see, there is a knot here or fillet here. So suppose if when you apply load, it won't be highly stressed here. So here this location we can defeature it if it is consuming more elements. So remember there is a small rounded shape here. This we can defeature it. Similarly, we'll be having small holes, and definitely they won't influence stresses in the geometry. So those holes also we can defeature. Suppose if user defeature this type of fillets, definitely that will be a modeling error. And then comes a discretization error. Uh, what exactly discretization error is? It's basically difference between mathematical model and FE model. So the mathematical model will have infinite degrees of freedom, and the finite element model will have finite degrees of freedom. So because of this uh, discrepancies, we will get a discretization error. So basically, finite element results influenced by number of elements and or element size, and of course number of nodes per element. So both are very important. Number of nodes per element and number of elements or element size. So what is the significance of this? these two things. So if I take a quad, so I can have 4 nodes or 8 nodes for this element. So FEM results influenced by number of nodes. Suppose if I take quad with 4 nodes, I'll get one result. One, and if I take 8 nodes, we'll get one result. And as we discussed more on this, this element with mid-side nodes or quadrature elements will have better convergence. So number of nodes per element definitely influence the finite element results. So this error can be minimized. We cannot avoid this error, but it can be minimized if it is correctly simulated using finite element modeling. So we should understand that discretization error cannot be avoided. It can only be minimized. So one of the important thing in error estimation is smooth stress. What is the smooth stress? So basically, the averaging stresses is based on evaluating stresses at the Gaussian points located in the within the element, and then interpolating the nodes using shape functions or of a specific element. So basically, whenever there is a element is there, so in finite element method, we can tell the Gaussian points. Suppose let us assume this element has 4 Gaussian points. So finite element method will give results based on Gaussian points. So the results will be interpolated back to node using shape functions. Remember the shape function. Purely shape functions are used mainly to define the displacements or results across the elements. That's what we studied and we discussed also. So we have a result at Gaussian points that will occur at the interior of the element, and this from this results it is back calculated to the nodes using shape. So then these stresses in all elements at common node are averaged or represent the stress at the node. Um, okay. So then these stresses in the elements in all elements at common node are averaged represent at the node. Suppose let us take this element or let us consider this node. This node is shared by this element and this element and this element. 4 elements are shared. This is a 2D element, 2D geometry, and one node is shared by 4 elements at this location. So this the stress from this element, this node will have stress from this element, this node will have stress from this element, stress from this element, and stress from this element. This node will be shared, will be having 4 different stresses. So all these 4 stresses on this node will be averaged. So it may follow weighted average. Weighted average in the sense it's basically the area or volume of the element will taken into consideration, and it will do the weighted average calculations, and it will assign the corresponding stress to the average stress to the node. This process is called smoothing process. So whatever the technique it followed is a smoothing process. So Yeah, and apart from this smooth stress, there is a general stress field obtained from this equation. So when smooth stress is performed, uh, so typically it will have the element will have two stresses. One is stresses from stress field, general stress field derived from this equation, and then there is a smooth stress averaged from the stresses, other shared element stresses, and there will be two different stresses: general stress field and smooth stress field. If they differ more, there will be some criteria will be there. The difference between general stress field and smooth stress field is more, then it requires a mesh refinement. So that is to understand like what is between the uh, average stress and stress field. So based on the definition of average stress and stress field, so we have a error estimation. This error estimation typically followed by most of the uh, softwares or finite element tools based on strain energy. So here there are three things are there in the strain energies. So factor. So first factor is related to the stress field. This UI is related to the this factor is related to the element stress field. Okay, element stress field is derived from this element stresses can be calculated in EPU. Okay. So in finite element method, stresses are calculated using this equation for this element. Apart from that, we'll be having smooth stress in the element. That is done by averaging. So second factor is related to smooth stress, and the third factor is related to the difference. The strain energy, third strain energy is the difference between stress field minus smooth stress. So this stress represents difference between the two stresses, element stress and smooth stress. Yeah. So these are the three important strain energies. So these strain energies are used to calculate the error in the finite element model. So this is the equation which we will be having in calculating the error estimation. So the top factor is difference in strain energy difference based on strain energy based on difference in smooth stress and stress field, and this is the smooth stress. This is the stress field strain energy, and this is the again same strain energy like strain energy related to the difference between the smooth stress and the stress field. So this is the equation which is used exclusively in most of the finite element programs. Um, so typically the mesh what we have should be having error less than or equals to 5%. If it is having 5%, then we can tell that this mesh got converged. So this is the equation to get a convergence in the convergence error in the finite element model. So what you can do is directly put a mesh and do the solution, and definitely like most of the tools will have this extracting this error. Then you can get this, you can check whether you got less than 5% or not. Otherwise you need to go for remeshing and understand what are the critical locations in the geometry, and you do the remeshing surrounding that location. Now let us look into a couple of examples in understanding this mesh convergence. Let us take a cantilever with a small notch here. So this cantilever is having these dimensions: length of 300 mm, height 20 mm, and width 30 mm, and a hole of half 10 mm. And the steel material properties are assigned, and we um, applied a force of 1500 newtons. So initially we solved with 7 element size. Number of elements are around 1000, and we used 8 noded brick element. So for element size 7, we got a maximum S1 of 500 MPa and error of 38. It's 38%. This is S1 stress, and this is SZ axial stress. That is along the length of the cantilever. So it is both are matching, because we'll be getting, when you are applying a bending load, your bending problem, and along z direction we'll get the normal stresses. So the error seems to be very high, 38%. Our remember our requirement is should be 5%. So when we try to remesh with 5 element size 5, we got around 32%. And this, please check on this number of elements getting increased as size reduced. And when we try to put element size 4, the elements are almost doubled, but error is not reduced. It's still 28%. So this, we need to go further refinement, and then I need to upload the document 1 minute. So we further reduced the element size 3, and error estimate came to 20%, and 2 the 16%. See the number of elements, how it increased. With 4 it is 3000, with 3 it is 7000, and with 2 it is 15,000. Still we are unable to achieve the error estimate. It's a 16%. Then we went with error element size 1, and it is almost close to 5%. So If you see here, number of elements almost it's 40,000 here. I could not able to write here. So with element size 2, it is almost 15,000, and here it will be almost around close to 40,000. I could not able to relate, but it is a more than double of previous mesh size. So here what I did is I have put a complete uniform mesh. That means any element within the cantilever will have size of close to 1 mm. But here, if you see here, maybe your picture is not clear. Okay, yeah, you see here the high critical stress is happening at the ID of the bolt hole. That means, so we are getting high stress here at this location. So instead of putting mesh everywhere equal, we can make a cut here, and we can put fine mesh here, and we can put very smooth fine transition mesh. So we are getting very high stress here. So what we can do is we can put very fine mesh 1 mm here, coarse mesh up with 3 mm or 4 mm, or we can put very transition mesh here, very fine. It should be having very good transition from fine mesh to coarse mesh. So that way we need to plan our finance. So that will reduce. So with uniform mesh, we get 41,000 something element size, element number of elements. Type of mesh we can reduce to 25,000 also. So this is how we need to follow our finite element modeling strategy to achieve the convergence. So that is one example, and this is another example on 1 minute. Let us take another example. It's a bracket. So here it is so this bracket is constrained over here and applied load here. There is vector applied at this location, and these are the geometry related details. This is a purely plane stress problem. It's not a 3D problem. It's a 2D problem. We have assigned a thickness of 3 mm to these elements. This geometry is meshed with the plane stress elements. That is plane stress with the thickness elements, and these are the geometry details. Steel properties are assigned. So here, not able to see properly. So first, this geometry is meshed with 8 node elements. That means brick with quad with inside nodes. So it is meshed with quad with mid-side nodes. So if you see here, I have used element size 3, and error estimation we got it 6.5 5. It's very close to mesh convergence. So next step what we have done is like we put element size 2 and it is less than 5% and this mesh got converged. It's very near. So next is like we tried with element size 1 and want to see what is the mesh convergence. So it is almost 1%. It is almost 1% here. So this is for plane 8 noded plane stress element. So if you see the number of elements, so for element size 3 we got 112 and element size 2 is almost doubled and element size 1 it's almost increased quite a bit, 9,900. Now let us look into the 4 node element. So we tried with element size 2, look at it, 24%. Remember that element size 2 we got convergence in 8 node quad element and here it's literally struggling with 24%. Then we meshed with element size 1 and the error came down from 28 to 14%. And look at the element size 901, it's same 227. Still we did not get the convergence. We need to look for better convergence. We need to reduce this value further up to less than 5%. So now we have put half element size, half mm, and the number of elements increased to 3600, almost 4 times number of elements increased. Even then we could not able to get the convergence, it is 8%. And then we further increased with the element size, decreased the element size with quarter mm and we got the convergence less than 5% and number of elements increased almost 4 times. See the advantage of 8 noded element versus 4 noded element. So with the quarter mm we got the convergence here. In 8 noded element we got convergence at the 2 mm. Now just I want to look at the convergent meshes, difference between the convergent meshes. Um, so for a 4 node quad element, we got convergence of 4.6% and number of elements 13,000. And here 8 node quad element generally we'll call plane 183 in ANSYS and 182 for quad 4 node and quad. So for 8 node quad element size is 2, we got the convergence less than 4% and see the number of elements 227. 227 versus 13,000. See the difference. See the difference between quadrilateral elements and the linear elements. Similarly, let us check with the same element size. between 4 node and 8 node. Let us check for element size 1. For element size 1, we got 14% of error with 900 elements. With same number of elements, same mesh size, we got error estimate of 1%, and see the difference, stress error difference, 24 versus 1. So this is the advantage of 8 noded mid-side nodes. So whenever there is a requirement in our finite element modeling strategies, for critical locations, it is always advised to put a mid-side nodes for better convergence rates. And just I want to recap on what we have discussed in previous sessions. So here for quadratic, if you put one element, it will, for example, if you take one element, or let us come here. So this is the actual distribution of the geometry or for a particular problem, and this curve represents a difference between this color, orange color, indicates actual curve, and this straight line indicates one element for linear approximation. That is for elements without mid-side nodes. Linear elements. For linear elements, this is how it will predict. So for quadratic, it will perfectly matches with the actual distributions. Some mismatch will be there, but it is very minimal. And if you want to get same type of results, we need to put multiple elements for linear elements. So that is what we discussed in a previous example. Like for quadratic elements, 8 noded quad elements, with 200 elements we got convergence, but in linear 4 node element, it took almost 13,000 elements to converge the results. So this slide talks about that study. So any questions, if you want, you can raise here. This will complete my discussion on finite element modeling. Moving on to next chapter. If you have any questions, please raise. So I'll be going to chapter 5 now. I'll be discussing on types of loads. So just I'll wait for some questions to be asked. Whatever we have discussed so far, please do raise the questions. If you don't have questions, please respond me with message. Then I'll move to the chapter. Any questions? Okay, I'll move on to next chapter. So typically, whenever if you see any structure, the structure may be subjected to three types of loads. One is concentrated loads, like point loads. Second one is surface traction or pressure will cause, and then body forces. So these are the three typical forces. And so one of the important thing to be understand here. So uh, as we see, so we usually we apply some point loads here. Sometimes we'll apply pressure here over the surface. So what finite element modeling will do is um, that it will back calculate all the surface and body forces and apply it as a nodal forces onto the geometry. This is an important thing we need to consider here. So here pressure is applied on this element AB or the length. So it is back calculated into FA and FB at the two nodal locations. The main reason is, so loads generally the calculations usually carried out at the nodal locations, and so it cannot calculate loads applied on the elements. So pressures and body loads generally applied on the elements, and so definitely they need to back calculate and apply it back into the nodes, those loads. So as we are very much familiar with this equation, global equation, where F is a global nodal forces, K is the stiffness matrix, and D is the DRU. Okay, some typo is here. DRU. So their displacement degrees of freedom of particular node. So this force vector consists of three types of loads as we discussed earlier. One is body loads, another one is point loads, and third one is surface loads. So these three loads are subjected by any subjected any structure. So coming to surface forces, so basically forces, the surface forces are nothing but pressure forces. They typically applied on surfaces. So it cannot be applied interior of the geometries. So it can be applied only surfaces of the geometry. So basically, this in this equation, Ts represents surface traction. Ns is the shape functions for on that surface. So and it will integrate over that surface. So for example, if you take this structure here for a 2D element, the surface is applied along x direction, and there is no surface applied along y direction. So here, what it says is there are two factors are there, two surface pressures are there, Px and Py. So Py is 0 here. So directly P is applied here. So this is the surface traction vector. So coming to the body forces, these forces may be because of two things. One is weight or mass of the body. Second one is inertia related, that is velocity. So whenever a body is subjected to G loads, so typically whatever analysis I so far, it are not subjected to G load. So if a body is subjected, so every part of the body will be having forces. Or if body is subjected to angular velocity or any other velocities, linear velocity, so they will subject to some forces. Angular velocity results to centrifugal force. So these are the body forces, and this equation is related to body forces equation. N is a linear function of x and xyz. Basically, This will determine the centroid of the particular volume. If we take a element, suppose if we take a triangle element, so basically it will calculate the centroid of that element and it will apply there. And there is no need to provide explanation on point loads. It's a direct application of the loads. The point loads may contain um, forces in three directions, that is Fx, Fy, Fg, and moments. Three moments, Mx, My, and Mj. So all these three loads can be applied as a point loads. Let us take a rotating flywheel. It is subjected to omega. So for this type of conditions, one is centrifugal force will be acting on this element because of rotation. Okay, about this axis it is rotating, and apart from that, there is a gravitational force because of self weight. There will be gravitational force acting on this geometry. So in analysis, we need to specify. Suppose if you do any analysis, until unless you specify, provide any angle, this one gravity, general acceleration, because the body is really falling in this direction. Let us assume this is z direction. Then we need to specify acceleration along z direction. So it will have three factors: ax, ay, az. So we need to specify a value here, 9.81. Then that that will take the body loads. That will be taken as a body load and it will be solved. It will account that G loads. Similarly, here also we need to provide that information of how much gravitational force it will be. We need to give for this problem. So if you don't give that gravitational problem, there won't be any gravitational loads or body loads related to gravity. So let us take this example, cylinder subjected to internal pressure. So basically the pressure applied here inside or here is completely surface, applied on the surface. This is if you want to do three-dimensional, so we need to create surface here, or we need to create a pressure on the inside surface, and we have to solve it. Otherwise, if at all we need to do two-dimensional analysis, that is 2D axisymmetric. So simply we can model this cross section here, cylinder cross section, and we should apply, we should not apply P here, but we should apply the pressure into 2 pi r value. So that value we apply here. So these are the two examples related to surface load and body load. And coming to body loads, uh, this I think we have already discussed. This is a repetition of that slide. I think that concludes my session. So any questions you can write to me here, and you can take. These are the manuals which I have referred while preparing this documents. Any questions? I'm open to answer. So please raise. If you want, you can use interactive session. JNTU Vijayanagaram, I switched on interaction mode. If you have any questions, please do raise. JNTU MT, I think you requested for to show slide 30 to 34. Any questions? So somebody is asking, JNTMT is asking, what do you mean by bug? Bug is it's related to purely software related. There may be minor issues while programming, while doing while they have done the programming. There may be minor issues with the software that we usually call it bug. So generally for there are a lot of aspects in the finite element modeling. If they ignore some of the things, that will result into a bugs. So most of the time for regular analysis, those bugs not be captured. But if you do very complex geometries and different types of analysis, usually that type of bugs will be erased. So even right now we are I have started working from ANSYS 5. Now it is almost 15 and 16 is coming up. So even in 14.5 also recently our team found out some of the bugs. So we keep on updating ANSYS India team. So they will in turn update their newer versions, remove those bugs. So there is explanation of a bug. It's very famous for software engineers, but this is related to our software finite element tool. So basically, it may result into either most of the time it will give inaccurate results. It won't stop solution but give inaccurate results. So one of the important thing, like I have sent PDF files to your JNTU Kakinada. I hope those documents reached you guys. Otherwise, please contact your coordinators getting those documents. So yeah, I have released almost five session documents, and I'll be releasing another set of documents. Okay, you got five sessions. Okay, very soon I'll be releasing other documents as well. So maybe in a week time, less than a week's time, I'll release other documents also. Thank you very much, and have a nice day. And we'll meet again on Thursday, and we'll continue on same topic, types of loads and boundary conditions. When will be mid? I'm not sure. I don't know whether I need to conduct. I'll check with our L&D team. But be prepared for the mid exams. Okay, I'm not sure whether I'll be conducting or your professors will be conducting. I need to check with our team, as well as our team will check with your professors and get back to you. Questions I'm open. You can raise. Otherwise, I'll call for the day and you can resume again on Thursday.